This video shows a simple calculator program which uses the keypad to enter decimal numbers. I'll also show the offline assembler program, which is useful for larger programs like this and saves having to manually convert the instructions into hex codes. You still have to enter the codes into PlasMa using the switches, but as we saw last time, the memory can be saved to a paper tape and later on to mag tapes and disk. A ToyA is impractical for a nice calculator-like display, although I'm sure someone will come up with one. The main issue is it can only display numbers, and these can only be one per line, so it would look quite messy if you wanted to display a multi-digit number, say like 1, 2, 3, 4, 5, as buttons are pressed on the keypad. The other issue is that the instruction set only contains add and subtract, so you'd have to use long-winded methods for multiplying and dividing, and we saw the multiplying one earlier, and these all take up precious memory space. So I've gone with ToyB, which has a dedicated multiply instruction, although division still has to be done the long way, and it also has PlasMa extensions to the teletype write function, so it can output ASCII characters. Right, so here's a quick demo of the assembler. I've just used a small program which adds two numbers together and displays the result. Anything prefixed by a semicolon is treated as a comment and is ignored. A percentage character is a directive for the assembler. This %s tells it how to interpret the source code. The instruction sets for all three emulations are different, so the assembler needs to know which one you've used. This one says it's emulation 1, which is ToyA. Now, there are a few other directives, but I've just shown one more here. The %d directive indicates the start of data definitions, as opposed to %c, which indicates the start of code instructions. Now, you can also use names to label addresses, and these can apply to data or instructions, and these are prefixed with a dot. So these names, num1 and num2, can be used instead of numeric addresses. And when you've written the source, you run the assembler from the command line like this. It creates a listing file containing the hex codes. This is the original source, which has been tabulated and numbered, and this column is the memory address and the 4 hex digits at that address. So these are the values you enter on the load switches one by one. So moving on to the larger calculator program, here's the source code. Now I'm not going to go into the fine detail of how it all works, but I'll just give an overview along with some more of the assembler features. Now if you've got several lines of comment, rather than prefix each one with a semicolon, you can bracket the whole lot with these curly brackets. Here's some usage instructions for the program and a list of register contents, and my attempt at a state table so I could get my head round how the buttons would be handled. Here we've got the source directive %2, which means ToyB, and then there's a list of assembly constants, or equates as they're sometimes called, and these are just names which represent numbers and can be used anywhere in the source for clarity, just like the labels I mentioned earlier. So for example, instead of loading a register with the value hex 2b, which is the ASCII code for a plus character, you can equate a name ch plus, or character plus, to the value 2b, and from then on use that name instead. Now here's where the instructions for the program start, and you can see some initialization of various registers, and then there's a section here which loops around waiting for a button to be pressed on the keypad, and when this happens the code jumps to this label called key pressed. It then decodes the button and takes action depending on the current state. And there are sections for the 4 main arithmetic functions. I've used a jump table for this, so there's the divide, which does repeated subtracts, then add, subtract and multiply, which uses the dedicated opcode called mul. And finally there's a data section. Now I've put this at the end, but you can put the sections in any order and use multiple sections if needed. So we run the assembler like this and we get the listing file. and you can see the equate statements now show the actual value which will be used. And here's the code as we just seen, address and contents. The listing file is also useful for debugging. Say you wanted to stop the program at a specific instruction, you could find the address from the listing file and set that on the break switches so the program stops when it gets there. Okay, let's enter all these values onto the load switches. Right, let's press run. The program is waiting for a button to be pressed. Let's try 1, 2, 3, 4, 5. The digits are appended as they are entered, and this is the bit which would have been impossible to do with ToyA. Now the buttons with letters represent plus, minus, multiply and divide. The hash button is equals and the star button is cancel. So let's add 27 plus 27 equals. Now you can either continue a calculation by entering an operator, so we could say plus 5 equals, or plus 3 minus 4 times 2 equals, or we can start a new calculation by just entering a new number. We'll say 12 minus 3. And you can cancel an operation and we start again. We've got negative numbers. And what about dividing by 0? Let's do divide 0 equals, and E means error. Okay, well it seems to behave in a reasonable manner, although it is limited to what can be held in a signed 16-bit register, which is roughly plus or minus 32,000. So I can't see it catching on, but it's a good exercise for those old grey cells. And talking of which, I said earlier we can save ToyB programs to paper tape, but the more astute of you may have spotted a small problem. And this program fills the memory to the brim. So where does the dumper program go? Answers on postcards only, please. I'll just have to turn it off. Okay, that's it for now. Thanks for watching.